is working. Okay. Well, I'm looking at the time. It is 10:30. I am going to get started, even though 5 people are here. This class usually has around 20-ish people, or at least 20 people are officially enrolled in this class. All right. So I'm going to get started, even though some people are still missing. All right, so this is the program that I am going to work on today in order to illustrate a few concepts that are important, okay? And most of those you also need for the homework assignment that you're going to get. In other words, we're starting to have programming homework assignments at this point, and I know many of you are wanting to get some programming homework assignments, and now we do have homework assignments. All right, so I'm going to download this file, okay, and just kind of stash it on my temp drive here. Okay, there we go. And replace the one that I already have. And then I'll copy and paste. Well, not so much copy and paste, but just kind of move my text window over here. And it is also worthwhile to note that this is a good time to get River Spider working. Okay, it may not be that simple to get it working, but it is a good time to get it to work. So let me first point out, how where the instruction is to get River Spider installed, and to kind of at least so that you can at least get it to work. So that instruction is in TTP ASM tools and techniques. So if you expand it, you won't see the ones that are hidden now. But if you go to TTP ASM code execution tracing, that will include the actual instruction of how to get River Spider installed. And it is a little bit difficult to get it to work across all 3 different operating systems. So if you are doing Windows, which most people are doing, there's specific instruction for using Windows. If you are using Mac OS, there's a section that only applies to Mac OS because it's actually a little bit easier. And there's also a video to show you how to do it step by step. So if you are thinking, okay, I cannot do this with only written instructions, I need to watch what the screen should look like, there's a video. And the video has kind of 2 parts. The first part is only applicable to Windows. The second part is applicable to any operating system. So I would at least watch the video and get an idea. So if you have Mac OS, you kind of skip to like about the 10-minute mark, and there's a different folder or different file for you to download if you want to use if you're on a Mac OS. So there you go. Okay, so this is the information that you need. The recording has already started, so people who are coming in a little bit late is not gonna lose out in terms of content for this class. All right, so there's really not a whole lot more. Okay, for this class, we still have structures to talk about, but other than structures, there's not really a whole lot more topics to talk about here. So we are pretty much all done, in terms of parameters and local variables. Today's lab is on function calls, and then you have a homework assignment to deal with function calls. So do we have any questions before we get started with today's lecture? Any previous concept that you want me to clarify or explain? Because all the concepts are stacking on top of each other, no pun intended. Okay, so that means if people have a kind of holy foundation with all this material, it will get extra difficult at this point in the semester. And the final exam is worth 40% of your total score. So it is a good chunk, okay? For most people, it is it's a good chunk of percentage. So if there are no questions, I am going to go ahead and start to talk about the actual content. So I am going to take a look at the program that's already posted, which is postinc.c. And I will also be looking at the TTP ASM, the assembly version of the same code. So we'll focus on the C side first, which is the left-hand side from your perspective. So on the left-hand side, we have postinc as a function that is written entirely in C and C++. It takes a pointer to an unsigned 8-bit integer. So even though in C++ you have pass by reference, there is no such thing in regular C. Okay, so when you're working with just regular C, you only have pass by pointer. If you want the function to be able to change the parameter, you have to pass the address of what you intend for the function to change, which is like in this case. So post increment is having its own local variable called old value, and old value is getting the original value that P is pointing to and make a snapshot of it. In other words, old value is, as the name implies, the original or the old value of whatever P as a pointer is pointing to. And then what we do is we add one, not to the pointer P, but to what it points to. And then we return the old value. So that's basically the same thing as what we know as post increment. So when you have an integer and you have plus plus after the name of the variable, that achieves the same result. Okay, but this is how we can kind of emulate the same effect, but only using just kind of normal coding without the actual post increment operator. All right, so in main, we have two local variables. One is x and one is y. X is the one that is initialized, and then y is the postinc of x, basically. So what do you think y should have? By the time we get to the return statement, what is in x and what is in y? X is the one that is experiencing the post increment, so it becomes 4. But the return value of post increment, which is 3, is going to be assigned to y. So y ends up with a value of 3, and x ends up with a value of 4. Okay, so that's my claim. And the nice thing about programming classes is I can claim everything that I want to claim, but at the end of the day, you can just test run it and find out whether it does what it is supposed to do. So I'm just going to compare postinc into a program and then run it through GDB. Okay, there we go. And we'll put a breakpoint on line 17. So I'm just going to run through the whole program and print what is in X, which is a 4, and what is in Y is a 3. So that just kind of verifies in my original observation of what this program is supposed to do. All right, so we get back to the editor and see if there are any questions before we actually start to implement the program. Are there any questions about the C code? So from here on, these 4 weeks or so, this is all we're going to do, okay? We look at C code on the left-hand side, and then we'll try to implement the C code in assembly code on the right-hand side. So that's kind of what we'll be doing. By the time, by next Monday or so, I'll be adding structures and arrays to the whole mix. But that would be the very last topic from the lecture perspective. And then after that, it's all just demonstration, how to write code. All right. So seeing no questions, I am going to start with the assembly code. So the assembly code is going to start with a no op because that's a bug in Logisim. You have to start with a no op instruction. And then the entry code is going to call main as if it is a normal function. That's because main has local variables, and local variables must exist on the stack. So I might as well just turn main into just a normal function. So that means I need to, well, okay, technically we don't have to do this, but I'm going to do it, which is to initialize the stack pointer to 0. The 0 is really a misnomer because it really is representing 256. But since we cannot represent 256 using only 8 bits, it is quote unquote seen as a 0. And then we get A to be the return address. I think we talked about this already in this class. .6 plus is basically the address that is 6 bytes after the LDI opcode of line 3 in this case, which turns out to be where the function needs to return to. So, I'll do the counting after this, okay? So decrement D, STDA, and then JMPI to main, and then we have the halt instruction here. So I claim that .6 plus on line 3 is the address of the halt instruction. So that has to do with the LDI opcode itself is at an offset of 0 from what that dot is referencing. And then the constant of .6 plus itself is at an offset of 1 byte after the dot. So this will be 2 bytes off. This is 3 bytes off. This will be 4 and 5 bytes off because JMPI or any instruction that has an I in it, that has an immediate component in it, will take up 2 bytes. So that means that makes halt 6 bytes away from the opcode of LDI on line 3. So we talked about this last time. The best way to visualize this part is to look at the assemble view of the assembler, which we can do once I test run this code in River Spider. All right, so we have postinc as a function. And from this point on, I'm going to use a very consistent way of defining where I can find the parameters and also the local variables in the frame. Okay, so I'm pretty sure we talked about the concept of a frame. Do you guys remember what is on a frame? What is in a frame? A frame has local variables, the return address, and all the parameters. Okay, so those things, collectively is called a frame. So in this case, the first thing, or where the stack pointer is going to point to is the old value local variable. So I'm going to say that, okay, this is at an offset of 0 from where the stack pointer points to once I have allocated for the local variable. And I might have some additional local variables in some other functions, but in this case, this is the only one. So LVS is the abbreviation of, does anyone remember, local variable size? Very good. Okay, so local variable size is the offset to find the very last local variable that is declared, plus the size of that same local variable, which only has 1 byte in this case because it's an 8-bit unsigned integer. So that's how I would systematically define where I can find the local variable. The next location on the stack is the return address. So typically we don't really need to access it, so we'll just kind of skip over that. And then we have one single parameter, which is p, which is a pointer. But at this point, I don't really care about the type. I just need to know where to find it. So in this case, it is postinc LVS1 plus, because this one here is referring to the size of the return address, because we have to skip over the return address to get to the parameter. So this ordering has to do with the caller-callee agreement, because we push the argument first, and then we push the return address. So that accounts for why we have this item here and why we have to skip over the return address. The local variables are all reserved by the function itself, and that because it has to do the reservation after the function has control. So that means the allocation of the local variable is pretty much the last thing that we do to the frame. And that's why the local variables end up with the lowest address in memory. So that's once we have this set up, we will then allocate for the local variables. And the systematic way to do this is to put postinc underscore LVS into a register, say B, and then subtract that from the stack pointer. In other words, normally when we push something, we would subtract from the stack pointer and then immediately put something into the location that we have just reserved. In this case, for local variables, until we have an assignment operation to the local variable, we just go like, I'm just reserving the space, okay? I'm not putting anything into the local variables just yet. I'm just reserving the space for the local variable. So that's why I'm only subtracting that much from the stack pointer, but I'm not putting anything into that space just yet. My way of coding is to always include the ending code. So if there's a certain structure to it, I always put in the beginning and the end all kind of at the same time. So this way I don't forget about the end. And then after this, we just do LDBD, increment D, and then a JMPB in order to return to the caller. So basically, after we deallocate the local variables, the stack pointer will point back to the return address. So lines 2, 20, 21, 22 is basically making use of the return address so that we can continue execution at the caller. Are we still doing okay so far? We're good. Okay. All right. So if there are any questions you want to kind of ask right away. All right. So the rest of the code is really line 6 and 7 of postinc in C. So now okay, so this is one question that some people have in my Tuesday, Thursday class is, okay, where do we start? Okay, how do I get started with coding? Okay, well, my answer to that question is you look at the dependency of things, okay? You look at what do I need in order to do this? Oh, okay, so that means I cannot do this until I have all of these things already done. And then you look at each of those things and you ask, okay, in order to get this done, what do I need? So we look at this whole thing and we say the assignment is the very last thing that we do, okay? Before we can do the assignment or the actual copying something to over something else, we have to figure out what is the right-hand side. So I'm not even worried about the left-hand side at this point because I just need to figure out what is the value of the right-hand side of the assignment. And in order to figure out the right-hand side, what do I need? Okay, this means we need to know the value that is pointed to by P. Okay, that's good. But before we can do the dereferencing, I need to access the parameter first. Okay, but how do I get to the parameter? Well, the parameter is sitting somewhere on the stack. Okay, I know the offset to it. That's all I know. So that means I need to get the offset first, turn it into an address, and then I dereference in order to get to the value of the parameter itself. Okay, so the whole chain of reasoning is based on dependency. Okay, this is what I need to do. What do I need? Oh, you need item 1 and item 2. Okay, let's look at item 1. What do I need to get item 1 do? What do I need in order to get item 1 done? Oh, item 1 requires item 1A and 1B. Okay, let's look at item 1A. So I'm just recursively applying this technique until I say, oh, okay, that I know how to do. And then we just go forward, based on that dependency list to go on to the next thing that I can do once I have, the first few things. So in this case, the first thing we do is we just get to, okay, I can use register A in this case. So the first thing is I just get to the offset because that's the one thing that is already known. Okay, the offset of old value is what we know. The way I would comment this is to say that A, register A, currently has the value of wherever old value is located minus the stack pointer. Because the subtraction of the stack pointer states that we just have the offset. We don't have the actual address. We just have the offset of where the stack pointer points to and how many bytes above that can I find old value. So that's what register A has at this point. And then the next thing we do is, oh, wait, okay, I need P, not old value, sorry. I wasn't reading the code correctly, but the same notation basically. All right, so how do I turn register A so that it is the address of P? Well, okay, if you look at math, if the original one is this this difference here, then if I add the stack pointer to it, don't you think your minus SP and plus SP will kind of cancel out, and then we just have the address of P left? So that's what we're going to do. Okay, so we just say add AD because D, register D, is our stack pointer. So by the end of the add instruction on line 19 at this point, A ends up to be the address of parameter P. So you look at your P and go like, okay, but that's not what we want. Okay, this expression is not asking about the address of P. It is asking about the dereference of P. Okay, so in order to do the dereference, I have to first get P itself. So that means I need one dereference so that register A is now the actual value of P. And then after that, I need one more to get to whatever P is pointing to. All right, so I'm just going to pause here a little bit and then see if there are any questions about line 17 to line 21, because lines 17 to 21 implements the right-hand side of the assignment of the C code on line 6. So your question can range anywhere from I'm not sure what this instruction is doing, within this context, all the way to how did you figure this out? Okay. So I tried my best, okay, to explain the process of how we look at dependency, and we start with the things that we already know, okay, and then we just walk forward with that. But that's I tried my best to explain that, but if that is insufficient, I can always try a different way. So yes. What 19 does? It adds the stack pointer to the offset of P from where the stack pointer points to. So we end up with the address of P. We end up with the address of P. But okay, so that's a good question. But from the fact that you're asking that question, I think your first question really should have been, how does that relate to line 17? Because you're not understanding what the label is, or at least it reflects that you may not be fully understanding what the label of postinc underscore P is representing. It is representing the number of bytes between where the stack pointer points to and where I can find P in the frame. Is that okay? All right. So now we have the right-hand side. You can finally work on the left-hand side. In other words, we have the right-hand side, we have the value. Where am I supposed to store this value? That's basically what an assignment operation is we want to store the right-hand side to whatever the left-hand side is specifying. The left-hand side is specifying the local variable old value. So it's kind of the same thing. LDI, I cannot use A anymore because register A is already used for representing the right-hand side. So I can only use the other two registers, which is plenty in this case. So now I'm doing exactly the same thing. I'm loading the offset of old value into register B, and then I add BD in order to get to the address of old value. And that's all I need because I'm going to store to old value. So once I have the address of old value, I can now store whatever the right-hand side has, which is already in register A, to whatever B is pointing to, because B is the address of old value at this point. I'm intentionally not adding the comments for this part here because that's I want you guys to be doing it. Okay, I want you to do it so that that's one more thing that you can do in order to help you kind of document and also to get an understanding of this code. Question? You look like you have a question, so I'm just gonna put you on the spot right here. Okay. Okay. You always use that to get the value of what you're referencing, right? Okay. So to answer that question, the best way to do it is to run it through River Spider so that we can actually see what register A has throughout line 17 all the way to line 21. So because that's a visualization tool, okay, we can actually see what is in register A step by step. So conceptually, it can be a little bit difficult to kind of grasp, at least for now. But once we run it, and you see how register A is getting changed, then you go like, oh, okay, now that kind of makes sense. Hopefully that that would be the result. So that means at this point, if you're the one asking the question, you might want to jot down the question, which is by the time we run this code, I want to have this question answered. Okay, so that's that's one value of taking notes in the class is you're not just writing down what I'm saying, you're also jotting down questions that you want to have answered. Now, it is up to you to decide, is this question directed to TAC in the lecture, or is it directed to myself so that I have to spend some extra time to kind of answer the question? That's up to you. But if you don't jot down the question, you're going to forget that question. Okay, so these are all really important things to capture when you are taking notes. Because anything that's on the projector is not too important because I'm double checking to make sure that I'm recording the right screen and also the audio is on. So so what you're really capturing should be your own thoughts, your questions, the connections that you have been making in your head, and so on. All right. You know what? I'm just going to put a halt instruction here. You're like, what? Tag, you're not done yet. Exactly. Okay. Because I suspect that this is already doing line 6 of the C code. Okay. Well, if it's not doing what line 6 is supposed to be doing, there is no point to continue with this development, right? So that's why when you are working on your homework assignment, you should do something similar. Okay. Because I've seen a lot of people thinking that, oh, I'll just kind of knock out the entire program and then I'll debug it all in one shot, hoping that the program is going to work perfectly the first time. I guarantee you it does not work the first time. Okay. I really cannot make that guarantee. I would say for 99% of the people, it's not going to work the first time. Even for myself, okay, I make stupid mistakes, everywhere. So the program is not going to work the first time. So this is a technique, okay, to gradually develop a program. Now this is made possible because of River Spider. So that means if you do not have River Spider, if you don't have it running, you are losing the opportunity to use I would think to be a very useful tool. It's a learning tool, it's a debugging tool as well. Okay, it's both at the same time. All right, so I have a very favorite mistake to make, which is forgetting to save the file before I run it. Okay, so I have to double check, remind myself, save the file first. Okay, so now I go to River Spider, and once I am in River Spider in the folder, I just have to point submit.sh to the source file that we just worked on, which is postinc.ttpasm. And I press the enter key, just let River Spider, the script, do all the magic. You can do this without the tool, okay? So I did make a grammatical or assemble time error, which is fine. I just have to go here, go to column B, and say, oh, okay, main is not even defined. Okay, that's my bad. I totally forgot about main. Okay, fine. We'll go back and finish main first. Okay, so main is going to be here. Oops, main. And main has its own 2 local variables. So same deal. X is the first local variable. So typically the convention is it has a lower memory address. There's no requirement that X has to be the one with a lower address and Y has to be the one that has a higher address. So this one is strictly just kind of convention, but it is not a part of the caller-callee agreement because local variables are only known to the function. It is not known to the caller, so it cannot possibly be a part of the agreement. Is that part okay? Does everybody understand how you want to arrange the ordering of your local variable is none of the business of the caller? Are we good? Okay, all right. So this is going to be main x1 plus. This 1 is referencing the size of x itself. Main LVS is going to be main y, which is the last local variable, or the offset to the last local variable, plus the size of the last local variable, which is the 1. So I know most of you are thinking, oh, why don't you just write your main x plus 1? Because the assembler can only understand postfix notation instead of infix notation. Okay, I'm going to digress a little bit here. I know some people really hate when I do digression, but that's kind of I do things when I remember to do things. So what I'll do is I am going to the assembler manual because I want to show you where you can find instructions of how to work with postfix notation because I think that might be helpful to some people. So unless you already have a really good understanding of what infix, how to convert from infix notation, which is what we are used to postfix notation, you might find the assembler manual to be helpful. Because if you go to that particular section, I now include a link of learn how to convert from infix to postfix notation. So this tells you the instructions so that you can do the conversion yourself. But if you say, I can do my best, but I don't even know whether I'm doing it right or not, then use the second link. The second link is an actual tool, it's a web-based tool to help you. You start with the infix notation, and it will do the conversion to postfix notation. So that way you can practice doing this by yourself. You go like, okay, I think this infix becomes this postfix expression here, and you can double check it by using the second link. So that's I think these are useful tools for you to learn how to use postfix notation. We are not going to be using like super duper difficult postfix expressions in this class, but it still can get more than just adding one to some label. Okay, so it is still a useful tool that you can utilize in order to learn how to do that conversion by hand. All right, so getting back to coding. Okay, so now we get to main. Same deal, we have to allocate for the local variables. So LDIB with main LVS, subtract that much from the stack pointer, and then I will do, I'm doing the lazy thing here. Okay, we add that much back in order to deallocate the local variables. So now, after this, we'll do the usual return code, which is from line 33 to line 35, copy to here. Okay, so now in between, I can now specify what I want to do. Okay, so from the perspective of main, line 15 and line 16 are the two things that I need to do. So the first thing I need to do is to copy the value of 3 to local variable x. Same deal, okay? So if you're thinking, oh, Tech, you're going to repeat what you just said a little bit earlier, except this time we apply to main x, the answer is yes, okay? So there's a certain pattern to this whole thing, okay? So recognizing that pattern is important, but I will not overemphasize the importance, because patterns are important, but you still need to understand why it works. Okay, so that part is still true. So I do add BD, STBA, but I'm forgetting to put a 3 into A first. So I just do LDI A3. So now I'm claiming that line 45 to line 48 is going to accomplish making local variable x of main into a value of 3. Okay. All right, so that's where we'll stop first, okay? Because until I know this is the right way to change the value of a local variable, the rest is useless, okay? So I need to double check that this method it will indeed work, okay? All right, so we'll go ahead and do this checking. I forgot to bring my tablet today, which is okay, I can still do it. So now we want to look at what location is what, okay? So the first location that we are using is location FF, okay? So location FF, which I designate as asterisk 0xFF to basically say what is the content of location FF, that is the return address to the entry point from main. So by the time we get to main, and we do the allocation. So by the time this statement is done, the stack pointer will be pointing 2 locations lower compared to FF. So that would be FE and then FD. So that means the stack pointer, which is register D, should be FD at this point. Oops, there we go. So that means also by the time I store something like 3 into register where register B is pointing to, which is local variable X, that would change location FD to a value of 0.3. I'm not using the 0x anymore because everything is just in hexadecimal by assumption. So this is my prediction, okay? It is important that you do this as well when you are debugging your program, that you have to know exactly what is supposed to happen by the time you get to a certain line. So this way you can check whether that is actually the case or not. Do we have any questions at this point? Now, yeah, question? Nope. Okay. So it took me a few minutes to figure out what location should be getting what and what should be in which register. It might take you 15 minutes or even half an hour, but that is not time wasted. because that is how you study. Okay, in order to get through the final exam, to get a reasonable score out of the final exam, this is exactly what you need to do, is to look at the instructions one by one, understand what each one is doing, and also to understand in the context of all of the other instructions, what do they accomplish together. So that's basically studying. Okay, I am just studying myself by dry running this program in my mind. Okay. All right, so now it's time to test it. So I go to River Spider and just gonna test run it. So hopefully I don't have any assemble time error this time. Okay, code is good, starting the simulator, and it's done. Okay, so now I can go to the assembler and go to the analysis tab. And well, okay, lazy as I am, I'm just gonna go all the way to the end and double check and see if I do end up with uh, putting a 0, 3 into location FD, and that's exactly what it is. Is that okay? And I'm not sure why this is cutting out all the comments. Because I think it is in the original code. Oh, maybe I forgot to save it. Let me double check. Yeah, I think that's what it is. I forgot to save the file with all the comments. So let me just run it again so that we can see how the comments is matching the actual behavior of the code. All right, so let me switch back to the assemble tab. Yep, there we go. We got comments this time. Very good. All right, do we have any questions about how to read the analysis tab of the assembler tool? What each column is representing? Are we good with that? Okay, all right. So what we have done so far is to go like, oh, okay, so we understand how to allocate for local variables. We know how to access our local variable in order to kind of initialize the value of the local variables. What about the map? Okay, what does it look like? Okay, in this case. So one way to visualize this whole thing, okay, I'm going to go to the regular shared folder and just add a spreadsheet because I don't have my tablet with me, so I don't have an easy way to draw a memory map. So I'm just going to draw it with a spreadsheet. So at location FF, okay, we store the return address. Location FE is allocated to local variable y of main, and then location FD is local variable x of main. These 3 bytes together is the frame for calling main from the entry code. Okay, because it consists of the local variables, the return address. In this case, we do not have any parameters. So these 3 locations together is the frame for calling main from the entry code. So we'll go ahead and kind of color code it a little bit. Okay, so I'm gonna just pick a color. Yeah, this is FD. Yep. So I'm going to use the highlight tool or the tool to change the color of a cell. Where is that tool? That one. Yep, there we go. Ah, wrong cell. Okay. There we go. Let's do that one more time. There we go. Okay. So these 3 bytes, okay, kind of belong together in quotes, okay? And that, okay, does that help explain things a little bit? Okay. So now the next question is, I'm still a little bit confused about how this whole thing happens. So the way we kind of clarify that is to follow the analysis tab this time. In other words, we say, how do we get the 3 into local variable x? Okay, this is how we load 3 into register A. It's just LDI A3. So register A ends up with a value of 3. Okay, that's pretty predictable right there. And then this one loads your main x as a label into register B. Main x is defined to be 0. So that means we are expecting register B to be 0. Okay, fine. And then the next instruction says, so let's add the stack pointer to register B. what is the value of the stack pointer? The last time we changed the stack pointer, we changed it to FD. So we are adding FD to 0. So that means register B is now also just FD, which is the address of local variable X of main. So when we store register A to where register B is pointing to, we basically end up performing the X equals to 3 initialization in the C code. Do we have any questions about this? So does this help answer the question that you had earlier? Even though it's a different block of code, this one is simpler. It doesn't have the referencing because we are not accessing a pointer or what it points to. Okay, so we're still good, hopefully. Okay, but there are a few things that are important here. We know that X is at the address of FD in this specific case. So we'll go back to the code, and then we'll make some note here, okay? So when we move on to the next instruction or the next statement in C, it would be y equals to postinc the address of X. So once again, how do we implement this? Well, let's not worry about the assignment, okay? Because the first thing I need to figure out is the right-hand side of the assignment. Until I have the value from the right-hand side, there's nothing to assign, okay? So now my focus is calling postinc. Then once again, okay, using the dependency analysis, you go like, what do I need to call a function? Well, this function this function call has an argument. So we have to pass the argument first, which is pushing it on the stack. So that's what we need to do. Okay, fine. We have to push the argument on the stack. It looks kind of complicated here. What are we actually pushing on the stack? What do we need to push that on the stack? Oh, we are pushing the address of X on the stack. But how do I know the address of X? Well, we kind of had it already in the previous instruction, so I could just push that register, okay? In other words, in this code here, register B still has the address of X at this point. So if I'm lazy, or if I want to do optimization, I could have just done this. This is basically pushing the address of X on the stack. I'm going to pause and see if you guys are making the connection that, oh, okay, that's a little tricky, okay, but it is an optimization because we already have the address of X in register B, and I need to push that address on the stack. Might as well just use it instead of recomputing it. Is that okay so far? All right. So once we push that, then the next thing we need to push is the return address. So the return address, I kind of need to specify that in. We can put it into register B or register A. It really doesn't matter. So I'll put it into register A. And now I made that mistake that was in the second exam. I used LD instead of LDI. So I just caught it because of syntax highlighting. And push it on the stack, decrement D, stda. And now I'm ready to go into the function, jmpi, to postinc. And then when it returns, which it should return to line 56, at which point I'm going to increment D in order to deallocate the argument that is still sitting on the stack. All right. So that means now I'm actually calling postinc, and there's a halt instruction in postinc. So I'm going to test the program as it is right now, and we go like, okay, are we going to get the current value of X into old value of postinc? Because that's kind of what we did earlier. Okay, the only portion of code that is done in postinc is implementing line 6 of the C code. Okay, so right now we want to find out, okay, are we actually doing that? But once again, before we do that, we kind of have to know what the stack should look like by the time we get to the halt instruction of line 27. So when we call postinc, we're pushing a bunch of stuff on the stack again. So that means the picture of what the stack should look like is going to change. So we are going to update our map here. Okay, so we go to, nope. I was looking up, how to do programming in the Unreal Engine because we might end up offering some classes in game development. But I think it might be meaningless to most of you because we won't get the curricula done until fall 2025. So by the time we actually offer the class, most of you would have graduated already. Huh? Not in game programming. That's not game programming. That's game design, which is different. Yeah, yeah, I know about that one because when we were developing our game development program, uh, Sac City protested. They go like, "Oh, you guys are stepping into our turf. You cannot do this." We go like, "But we are doing development. We are not doing game design." They do not seem to understand. It's okay. All right, so we are. I'm just populating the addresses. So when we call postinc from main, we have to push one thing on the stack. So we first push the address of x as the argument, and then we push the return address from postinc back to main on the stack. And then we have to reserve one local variable, which I called old value, on the stack. So that means in this case, these 3 bytes become the frame of the invocation of postinc. So now I'm gonna color code it in a slightly different color. Okay, maybe slightly blue like that. So is that okay so far? So column B is telling us what role is the value of that byte doing, but it doesn't tell me what value it has. So right now, in terms of the value, we know X has a value of 3 already, okay, because I just put it there. We also know the address of X is going to be 0xFD, okay, because that's the address of X in main. The return address is, we don't really have to know, okay, because that kind of depends on every time I change the code, that address gets shifted around a little bit. So I'm not too concerned about that. Old value should end up, as the value of x. So we are expecting a 3 here, but I'm going to put a question mark here because that's what we're going to check. Is that okay? So I am testing the program step by step, okay? I get certain things done so that I can confirm, okay, this is the right way to access a local variable. So once I confirm that, then I go like, okay, I can reuse the same template of code when I need to. But right now, I have something more complicated to do because it involves getting to a parameter, which turns out to point to some particular value, and I need to copy that value, which is pointed to by a parameter, to a local variable. So now I kind of have this question here, are we getting this done? Because if I cannot get this done, there is no point whatsoever to continue with writing the rest of this program. So what do? We just go to River Spider, okay, and we just say, okay, let's test run this again. Okay, if you have River Spider installed, in any reasonable operating system, the command line interface would just allow you to use up arrow key to repeat the previous command. So it becomes like that easy to run the program again. All right, the object code is good. Starting simulator. Okay, we are all done here. So now we switch back to the spreadsheet. We go to the analysis tab. Okay, so first go here, go to the analysis tab, and okay, I think I just made my famous mistake of forgetting to save the file first. Now, how can I confirm that? Okay, it's always good to confirm that this is all that was. Okay, that it wasn't because of something else. So in VI, Control G will tell you the current state of the editor. So it's telling me that the file has been modified but not saved. Okay, so I have just made my usual mistake. Okay, so now I save it, and now I have to rerun it. Okay, so there we go. If anyone wants to integrate this tool chain as an extension to VS Code, feel free to do so. Huh? I have no idea. I have absolutely no idea of how to um, create your own extension to VS Code. I would suspect it's not that difficult. Yep. All right. So now if we go to the tool, it does proceed a little bit further, blah, 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 blah. And if I am lazy, I'm going like, okay, FA, okay, the location FA should get the value of 0, 3 according to our prediction. So let's double check our prediction here. This 3 is supposed to go to location FA. Aha, that works. So the question mark goes away. But to answer your earlier question, okay, about that sequence of instructions, right? Let's go check that out. So the question was from line 17 to line 21, exactly what we are doing over here. Why do we end up with whatever P is pointing to by the time we are done on line 21? That was the question. So the nice thing about the River Spider, or to be more exact, the Analysis tab, is it does show you everything that you need to know. So basically, we're looking at line 17. This is the instruction or the actual source code on line 17. This is the effect of line 17. We put a 2 into register A. Does that make sense to you? That parameter P is 2 bytes away from where the stack pointer points to at that point of the program. How do I know? Tech, have we talked about this? Yes, we did. If you look at this picture, this is where the stack pointer points to. Okay, so if you have to draw like where the stack pointer is pointing to, it's right here. So where is parameter P? Parameter P is this byte over here. This is D plus 0, this is D plus 1, this is D plus 2. So the offset of 2 is indeed correct. All right, so let's go back to the trace again. So we have a 2 here, and then we say, okay, but wait, the 2 is just an offset. It is not the address. To get to the address, we have to add the stack pointer to the offset. What is the stack pointer right now? The last time we changed the stack pointer, we changed it to FA. FA plus 2 is FC, so that's why register A is now FC after we add the stack pointer to the offset. So are we okay at this point? Okay. So the key concept, the key concepts that you have to differentiate in this case is what is an offset to a certain thing in the frame and what is the address of the same thing in the frame.
So we're saying that we're first getting the offset, then getting the reference, the pointer to the address, and then we add the reference.
And then we, well, yeah,
to get the value.
To get what P points to. Well, to get to P first, and then to get to what P points to.
Okay.
Yep. So right now we have the address of P in register A. Now, is that matching what we are expecting in the picture? Well, the answer is yeah. This is location FC. This is where parameter P is located. So we do have the address of parameter P in register A right now. Okay. All right. So to continue with this whole thing here, the next thing we do is do a dereference. Okay, LDAA is basically dereferencing A, and put the dereferenced, the result of the dereferencing back into register A. In other words, we're asking and say, oh, okay, follow where A is pointing to, go to that location, grab that content, and put that thing back into register A. So if we look at the actual code execution, so register A had the value of FC, so that means we're going to the location FC, take whatever content is at location FC and put that back into register A. So when you look at the map here, what is supposed to be at location FC? Oh, okay, it is supposed to be the address of X, which is FD. So we should end up with FD in register A after the first LD instruction. So when you look at the actual trace, that's what we end up with. Are we still doing okay so far? Okay, so in class, okay, because I have to flip between a few screens, it is there's less continuity than compared to you doing this with two screens side by side, or doing this on paper where you have one piece of paper that is visualizing what is on the stack at the memory locations, and another piece of paper so that you can actually just follow the code and comment what happens by the time you get to a certain instruction. So when you do your own studying on pieces of paper or on a larger screen with multiple windows, it gets a little bit better. Okay. All right, so then what do we do? Well, register A now has the value of P, but P itself is a pointer. And the C code says, I don't want parameter P, I want what it points to. So we just have to do one more dereference, okay? So one more dereference means now we have to go to location FD and get the content, the value at location FD, and then retrieve that. So according to our picture here, oops, not this one, right here, location FD is local variable x of main, and currently it has a value of 3. So that means now we should end up with a value of 3 in register A. And that's exactly what is happening, because this is the outcome, this is the result of executing the LD instruction on line 21. Is that still okay?
Is it possible to see as a link,
Hmm?
sort of as a link to
You
access that
can,
value?
yeah, well, okay. So you can look at an address like a URL. Okay, the URL itself is some kind of value, right?
Oh, sorry,
It's
I meant as a sort of like the starting of a linked list, for example, because you have something that's pointing to the same address.
it is related.
Okay.
I think it's the other way around. Okay, the um, how you start a linked list is an address to a particular structure.
Correct.
So that would be the better way to describe it. I think you meant exactly that, but I think it goes the other way around. A pointer is a more general concept compared to the head of a linked list.
Right.
A head of a linked list is a particular application of what you can do with a pointer. Yep. Mm-hmm. All right. So that explains the right-hand side. What about the left-hand side? So the left-hand side is kind of the same thing. We load the offset of where we can find old value from where the stack pointer is pointing to into register B. That turns out to be a 0, which means, oh, we are expecting the stack pointer to be pointing to old value, at this point. So we double check that. Okay, so we go like, oh, okay, yes, indeed, the stack pointer is pointing to old value, which turns out to be FA. Well, let's double check that. Let's double check that the stack pointer is FA at this point. So now we go to the last time we update register D. Oh, okay, it is FA. So are you guys starting to see the value of using this particular tool? Because at any point of the execution of this program, you can actually work out exactly what is in each register and what memory location you have changed, and also what those values are. Now, is it easy to find that out? Well, I wouldn't say super handy, because you still have to kind of go, last time we changed it is what's here. It had a value of FA. Or what did we put on the stack? You kind of have to follow column C in that case and kind of go back up a little bit. But it is all there. Okay, the information is all there to begin with. You just have to work with the spreadsheet to find the information that you need. And then the next instruction says, okay, since register B had the offset to old value, if I add the stack pointer to the offset, I would end up with the address of old value. So FA is supposed to be the address of old value. And we can now go back to this slide here and say, oh, okay, it really is the address of old value. Okay, all good. And then we do the store. Register A has a value of 3 because this is the last time we changed register A. Register B has FA. So when you store DA, not DA, BA, then we are basically storing a 3 to location FA, which ends up with a 3 over here, which is also confirmed by column C, because column C says, uh, location FA just got a value of 0, 3. All right, so I'm going to do a pause, okay, and you guys can request additional time if you want to. And I want to see if there are any questions at this point. It, it can be a question about the concepts that are involved here. It can also be a question about the process of how I figure this out. I think some of you are taking calculus, so I'm going to use the analogy of calculus to kind of emphasize why those two types of questions are important and why one type is actually more important than the other one. If I'm asking you, do you understand the content? That is about the y value in the graph, okay? When I'm asking, do you understand the process to get this result here, to get to know how to derive this code, I'm asking about what is the first derivative of the graph, okay? So those two concepts are related, but I would say, knowing about how I come up with the solution, my thought process is more important. Because if you have the thought process down, you can reapply the thought process to many other problems, most likely outside of the context of this class. So to me, that is something that is more important to learn, but it is also something that is much more difficult for me to teach. So are we still doing okay at this point? Shall we continue and try to finish the program? Okay, all right. So now we switch back to the code here and we go like, okay, now I can remove this halt instruction. And then we will try to implement line 7. So line 7 is a plus equal, which is in C++, it is called a compound assignment operator, which basically means it's the same thing as whatever p points to is going to be 1 added to itself. Okay, so we're just incrementing it. So that means I think we need to know what location p is pointing to. Let's see, do we still have that information? I don't have that information anymore. So at this point, instead of confusing you guys and try to optimize the code up here so that I can put it in register C and stuff like that, I'm just going to redo the computation, okay? The one is not the one that I need to worry about much. It is the left-hand side that looks a little bit icky. But we have something like this already. So that means we already know how to get to it. So let's go ahead and just repeat all that stuff, okay? We get the offset, we get the address, and that's it, okay? Oh, wait, that's the address of P itself, okay? That's ampersand P. So we have to get to P itself. This is P. And if I do one more dereference, it will be whatever P has, okay? But that's not kind of what I need to do, okay? Or at least I don't want to use the same register. So I'm using a different register this time, okay? So I will comment this one, okay? Because B is whatever P is pointing to, A is P itself. Is that okay? For the most part, this is a repetition of what we did already. It's just that this time I need to maintain the value that P is pointing to, as well as P as a pointer itself. Why do I need to do that? Because once I add one to whatever P is pointing to, I have to store the sum back to whatever P is pointing to. So that's why I need two registers in this case to get this done. Okay, so which one should I increment? I know I'm supposed to add one, but which one am I adding one to? Am I adding one to register A, which is the pointer itself? Or am I adding one to register B, which is what P is pointing to? What does the C code tell you on line 7? So we're adding one to what P points to. Okay, so then we which register again? Register B, very good. Okay, so register B after line 31 is one more than what it used to be, but I'm not done yet because I have to put it back to where P is pointing to. So a store instruction is kind of what I need to do. So that completes the operation. Well, the interesting part about this operation is I am not changing anything that is in the frame of the postinc. In other words, if you look at the picture here, I'm not changing any one of the blue cells. I'm changing this cell over here. Okay, so that's the important part. So I can, probably do a halt here and then just double check everything, but I'm fairly sure that it works. So I'm gonna continue with the rest of the code. So the rest of the code is just returning old value. Okay, so this means I have to put the value of old value into register A, and then I'm all done. And then I can just deallocate the local variable and then go back to the caller. So that means LDIA post inc old value. By the way, the assembler is case insensitive, so I really did not have to fix the casing, but it just looks more consistent this way. Add AD, LDAA, and I'm done. That's because that would be by the time I'm done with line 36, register A is going to be the value of local variable old value, which is at the right place because any scalar type should be returned through register A. All right, and the rest of the code is already done. Okay, so this is kind of what I like to do is if I start something, if I know what the end is supposed to look like, I will put the end right away, and then I just go back and insert code between the beginning and the end. I do the same thing in C code. If I have open brace, I automatically close the brace and then I go back up to fill in whatever is supposed to go between the braces. Okay. Sometimes I do that with parentheses in an expression, but not always, because parentheses for simpler expressions, I can actually track that in my mind. But for anything that's more complex, I would do the same trick too. That's more like just programming practices that I find useful for myself, but other people may not find it as useful. All right, so now we can run the code. I think I did, but I didn't finish the entire code. So main is not all done yet because I didn't save. I did not put the result of postinc back into local variable y in main. That's okay because I should still see a 4 over here. In other words, I should still see location FD updated to a value of 4 in this case. So now I'm going to double check. Okay, just kind of scan down here. Aha, okay, we got it. And the stack should still be balanced, even though I did not put anything back into Y. So that means register D should get back to 0, 0, and I should get to the halt instruction in the entry code. So that's still all good, but I'm not done with the program yet. I'm not done with the program because I implemented the function call on this side, but I never finished the actual assignment itself in main. So now I have to go back and finish it up. Okay, there we go. So that point is going to be right after we come back from postinc and deallocate the argument. So right here is where register A contains the return value of postinc, and I'm supposed to store that value in register A to local variable y of main. So that means I need to compute the address of local variable y. So by this time, you guys are probably getting a little bored because it looks kind of the same as most of the other code when you need to access something in the frame. So that would be register B at this point on line 68 is the address of y. So I just need to store BA. So then y would become 3 in this case. So that should complete the entire program. So when the whole program is completed, when you look at this picture, that means this 3 should become a 4, and then this location here should become a 3. So I'm gonna try to denote that. Okay, so we'll do a 3 and then a 4, highlight this, and then do a strike out. Text, strike through. There we go. I'm guessing it cannot strike through just one part of it. That's just my guess. Let me try again. Text, strike through. Nope. Uh, is that okay if I just turn this into a 4? Okay. All right. So this is what I'm expecting to see on the stack is a 3 at location FE, a 4 at location FD. Okay, so we'll double check. We'll see. The 4 is already confirmed. So we are really just confirming that a 3 should go to location FE. So switch back, make sure I save the file, and then run it. There we go. All right, so now we switch back to the spreadsheet, go to the trace analysis, and there we go. Okay, that's the store of a 3 to location FE. So the whole program is done. Okay. So just to recap, okay, what we have talked about today and what you should have been taking notes about, okay? There are a few things. The first one is how do we access something on the stack, like a parameter or a local variable? That part has been discussed already. So if you say, okay, I got that down already, I'm good. Okay, that's fine. You don't have to take notes today about that. And then there is also, I think this is the first time we talk about local variables. No, it's not. Okay, when we talk about frame, we already talked about local variable. So that part is not new either. Okay, nor is the concept of a frame. So what is new today? The approach of writing programs. Okay, don't try to write the entire thing in one single swoop. Okay, because your homework assignment, which is due in 2 weeks, okay, is easy in a way, but it is also difficult in a way. Okay, so the first thing you need to do is to ask yourself, can I confirm that I have the right value in this register, and that value is supposed to be just the parameter itself? So you have to confirm that first, because until you confirm that you have the parameter in a certain register, you cannot make use of that parameter. Is that okay? So I would advise people not to write more than 3 to 5 lines of code at once. Okay, write 3 to 5 lines of code. Think about what those 3 or 5 lines of code is supposed to do in terms of memory location, content, what is supposed to be in which register, how the stack point is going to change, and so on and so forth. Use River Spider. Okay, confirm that first. If that is not confirmed, do not proceed any further. Okay, fix the program first. Some of you may need a lot of time to work on this program. Okay, it will get better. Okay, because every time you find out that, oh, I thought this is going to do blah in this program and it's not doing it, guess what? You're learning, because you're basically noticing that, oh, okay, my understanding of how the stack is organized, where the variables are located, where the parameters are, what each instruction is supposed to be doing. Maybe there are some holes and I'm misunderstanding certain things. Running the program will find out all the misunderstanding. Okay, so by locating where the problem is and fixing the program, you are studying. It is probably the best way to study for this class, or I would say just about any programming class. Okay, is to kind of make mistakes, because when you make a mistake, you are exposing a certain misunderstanding or lack of understanding in some cases of a concept. So that gives you a chance to go like, oh, okay, I'm not getting this. Okay, let me read some material. Let me revisit the lecture. Let me look up what the instruction is supposed to do in the opcode table in order to clarify and find out what is going on when the program is not behaving the way it is supposed to be behaving. Is that okay so far? So I'm just talking about the approach of how to get started with the homework assignment and how to kind of move gradually through the homework assignment. Okay, don't be too ambitious. In the first attempt. Okay, just go really slow. Okay, to go fast, you have to go slow first. Okay, that's what I learned when I took my car to the racetrack. That's what my instructor said. Okay, in order to go fast, you have to go slow. Okay, I want to explain that. Okay, even though we are not learning how to drive really fast on the racetrack, the reason why driving slow is how you learn to drive fast is because when you're driving fast, you get all this adrenaline rush. in the case of programming, you get all the anxiety, which is a different hormone, but nonetheless, it still affects your cognitive capabilities. But when you're driving slow, you go like, I'm not in any danger of crashing or anything. I'm observing, okay? How close am I to this apex here? I'm listening to my instructor, okay? You have to start to slow down by the time you get to these checkers, okay? Okay, registered, okay? You're supposed to hit this particular apex point before you start to accelerate again, okay? Okay, register. Because your mind is not busy going like, oh, I'm sliding already, I'm losing control of the car. You are still in 100% of control of the car, you're going slow. But you're capturing all that information that you need in order to go fast, okay? So the second round, you go a little bit faster, okay? Because you're gradually trying to learn the traction limit of your car, of the tire combination and whatnot. Okay, you don't even have to be driving a race car to kind of go through the process. You can be driving a minivan front wheel drive, but you're still trying to learn the limit of your car, traction limit, steering limit, and so on. It translates to coding as well. Okay, when you go slow, you're paying attention to all the details. Okay, what is in this register? Okay, why am I going to that location of memory? Why is that location of memory changed to this particular value? You're paying attention to all that stuff. So you're slowly building a model of how a program is supposed to function in your head. So once you have that model working fairly well, then you can start to code faster because now you can go like, do I have to run this through Logisim just to confirm this? Nah, I got this down. Okay, so now you can go a little bit faster. So is that okay? Is that analogy working out? Okay. All right. So with that said, I don't really have anything to add in today's lecture. So I just want to see if you guys have any questions. So we do have a lab today. Okay. So in other words, there are two parts to this program. The lab itself introduces some of the concepts, okay, that you probably know already at this point. And then there's a submission part that is due in 2 weeks, where you have to finish the program and turn in the program code. 2 weeks sounds like a lot of time, but it's not because we got Thanksgiving. Okay, and most people travel a lot and they have family get together, so that whole weekend is blown. Okay, so don't think of it as a lot of time. I would just kind of get started as early as possible when your brain is still retaining a lot of the stuff that we just talked about today. Okay, so that's just how I think would be the best way to proceed. You guys can choose however you want to proceed at this point. So I'm just going to show you guys where we are at. Okay, this is the activity for the lab portion. So this is the portion that you have to get done today, and this is the portion that you have to turn in or submit by December 4th, right before the lecture of this class. So that will be 10:30. Do we have any questions about how the assignment, quote unquote, assignment is set up? Which part is due today? Which part is due 2 weeks from today? How many people? Yeah, go ahead.
What else are we covering? So we're
Structures.
right now, and what else do we got left to cover?
Structures. So on
Structure meaning
struct,
extract and
C.
okay.
So if you want to be ready for the next lecture, which is next Monday, it will be on arrays and structures. Let me see if this link is already updated because I changed the link already on the other one. So I'm going to update this first. The old one still has most of the information. It's just that the new one has more. It's a more complete treatment of the subject matter. So I think it's that, and that should be fine. Update, refresh, and that's. I wouldn't say it's a really, really big topic. It really just has to do with how memory is utilized when you have structures. So this is the next one. Okay, I can give you a preview of what that looks like. So it basically just talks about arrays and how we do indexing, with arrays. And then it talks about structures and how do we access members inside the structure. So that's basically what we'll be talking about on next Monday. I do have to give people a warning that we're going to have overlapping programming assignments. So by next Monday, I'll give you the programming assignment of the recursive one. So getting one particular program done as early as possible is a good thing because then you can basically focus on the next programming assignment instead of having both kind of ongoing at the same time. So we might end up with 3 programming assignments, okay? Because I still need to give you one on structures so that I can legitimately put that in the final exam. But it is actually an important topic too. So that's kind of what is going to happen for the rest of this semester. Are we? Do we have any questions? Do you guys have any questions? Questions? Okay. So hopefully everything is falling into place at this point. If you need to talk to me, go ahead and talk to me, during my office hours or during the lab. If you need privacy, then go to my office hour. So that's all I can say right now. You should be able to get started right now because I think it automatically releases by 11:50. So the lab that you need to do is called function calls. You need to know the access code, or maybe not. This one does not have an access code. Are you guys in already? Okay, so there's no access code. Okay, cool. Alrighty, so I'm gonna stop the recorder and upload the recording as soon as